Dear students, welcome to the first lecture of Module 2 Fourier series. In this lecture, we will see what Fourier series are. A Fourier series is nothing but an infinite trigonometric series. That is, Fourier series is an infinite series containing trigonometric functions, sines and cosines. The French mathematician and physicist Joseph Fourier first used Fourier series in his work in which he developed the theory of heat conduction. This series had a deep influence in the further development of mathematics. So this series is named after his name and called as Fourier series. So to introduce a Fourier series, first of all, we shall recall the definition of periodic function. So what do you mean by a periodic function? A function f of x is periodic if it satisfies the condition f of x plus t equal to f of x. Here t is called the period of f of x, where t is the least possible value for f of x plus t equal to f of x. If we take a function to be sin x, then sin x has period 2 pi. Since it satisfies the condition f of x plus t equal to f of x with the t equal to 2 pi. But it is not necessary that every function has to have period 2 pi. Function can have any period, any arbitrary period. Suppose we take a function f of x with the arbitrary period 2l. So, a function is having period 2l means it satisfies the condition f of x plus 2l equal to f of x, and function is defined, suppose function is defined in the interval a comma a plus 2l. Then we will have Fourier expansion of f of x as f of x equal to a naught by 2 plus summation a n cos n pi x by l plus summation b n sin n pi x by l. For both these summations, n varies from 1 to infinity. Corresponding to the first summation, we will have terms like a1 cos pi x by l, a2 cos 2 pi x by l, a3 cos 3 pi x by l, and so on. And corresponding to the second summation, we will have terms like b1 sin pi x by l, b2 sin 2 pi x by l, b3 sin 3 pi x by l, and so on, by taking n equal to 1, 2, 3, etc. Now, here Fourier series is nothing but constant term plus sum of cosine and sine terms. A naught, the constants a naught, a n, b n are called Fourier coefficients of f of x. To compute Fourier series of any function f of x, we need to first find these Fourier coefficients a naught, a n, b n, and we will find these Fourier coefficients from f of x by using Euler's formulae. So, what are Euler's formulae for finding a naught, a n, b n? So, formula for finding a naught is 1 by l integral from a to a plus 2l f of x dx. Formula for a n is 1 by l integral from a to a plus 2l f of x cos n pi x by l dx. And for bn is equal to 1 by l integral from a to a plus 2l f of x sin n pi x by l dx. Note that in these formulae, all these three formulae 2, 3, 4, the limits for the integrals are a and a plus 2l, and these are nothing but the endpoints of the interval a comma a plus 2l. So function is defined in the interval a comma a plus 2l, and the limits for the integrals in all these three formulae are a and a plus 2l, the endpoints of the interval a comma a plus 2l. Next, we will see whether any function can be expanded in a Fourier series, and if yes, under what conditions a function can be expanded in a Fourier series. Let us see this. Any function f of x can be expressed as a Fourier series a0 by 2 plus summation n from 1 to infinity an cos n pi x by L plus summation n from 1 to infinity bn sin n pi x by L, provided it satisfies three conditions, namely 1. F of x is periodic, single valued and finite. 2. F of x has a finite number of discontinuities in any one period. 3. F of x has at the most a finite number of maxima and minima. These three conditions are known as Dirichlet's condition. So, if f of x satisfies Dirichlet's conditions, then this Fourier series 1 converges to f of x at each point where f is continuous. That is, if f of x satisfies Dirichlet's conditions and if f of x is continuous at x, then this Fourier series will be equal to, the sum of the series will be equal to f of x. Now suppose f of x is discontinuous at some point, say x equal to x naught. If you look at the graph of such function, okay, then there will be a finite jump in the graph corresponding to the point x equal to x naught. But the right hand side limit and left hand side limit exist and are but they are different. In this case, the Fourier series of f of x will convert to f of x naught. Okay, so here what is f of x naught? If x naught is the point of discontinuity, the value of f of x naught is given by half of f of x naught plus f of x naught minus, where f of x naught plus and f of x naught minus are respectively the right hand side limit and left hand side limit of the function f of x at x equal to x naught. Now, before solving problems on Fourier series, just take a note of it. While finding the Fourier coefficients in most of the problems, we have to perform integration of a product with the first function as a polynomial in x. In such cases, this Bernoulli's rule of integration by parts will be helpful. What it states, the Bernoulli's rule states that integral of product uv of two functions equal to u into v1 minus u dash v2 plus u double dash v3 minus etc. That is, integral of product is equal to first function into integral of second minus go on differentiating the first function and integrating the second function, signs alternately positive and negative. Also, try to remember these results. The value of sin n pi equals to 0 and the value of cos n pi is equal to minus 1 raised to n, where n is an integer. Now, let us solve some problems. So, here, first question, find the Fourier series of the periodic function defined by f of x equal to 1 minus x square in the range 0 less than x less than 2. Here we are given the function f of x equal to 1 minus x square and we need to find the Fourier series of this function in the interval 0, 2. So for this, we will first write the Fourier series of function f of x having period 2l in the interval a plus 2l. So f of x equal to a0 by 2 plus summation n from 1 to infinity an cos n pi x by L plus summation n from 1 to infinity bn sin n pi x by L. So note that from this interval a plus 2l we will get a plus 2l minus a. What is a plus 2l minus a equal to? It is equal to 2l, which is nothing but the period of given function. So for the given problem, how do you find the period of function f of x 1 minus x square? We take 2 minus 0. which is equal to 2. So we have the period of the function is 2L equal to 2. So we can write L equal to 1. So substitute the value of L in this general Fourier series. So we will get f of x equal to a0 by 2 plus summation n from 1 to infinity an cos n pi x plus summation n from 1 to infinity bn sin n pi x. Next, we find a0, an and bn using Euler's formulae and then substitute again in this series. So, what is the formula for a0? a0 is equal to 1 by L integral a to a plus 2L f of x dx. Euler's formula is a0 is equal to 1 by L integral from a to a plus 2L f of x dx. But what are a and a plus 2L? It is 0 and 2. So the formula becomes a0 equal to 1 by L integral from 0 to 2L f of x dx, that is 1 by 1 integral from 0 to 2 1 minus x square dx, that is integrating integral of 1 is x, integral of x square is x cube by 3. Then substitute the limits. First substitute the upper limit x equal to 2, then put x equal to 0. On simplifying we will get a0 equal to minus 2 by 3. Next we will find an using formula 1 by L equal 1 by L into, or an equal to 1 by L into integral from 0 to 2L f of x cos n pi x dx. General formula is 1 by L integral from a to a plus 2L f of x cos n pi x by L dx. Take L equal to 1 and a plus 2L are 0 and 2L. So substitute for L, I will get this. Okay, next integrate 1 minus x square cos n pi x using Bernoulli's rule. This we have, it is of the form uv, where u is equal to 1 minus x square and v equal to cos n pi x. So using Bernoulli's rule, integral uv dx equal to u v1 minus u dash v2 plus u double dash v3 minus etc. So the first term will be u v1, that is 1 minus x square into v1. What is v1? Integral of cos n pi x. Integral of cos n pi x is sin n pi x divided by n pi. Integral of cos n pi x is sin n pi x divided by n pi. Then minus u dash v2. Okay, what is u dash? U dash is derivative of u, derivative of 1 minus x square. It is minus 2x. Okay, then v2. What is v2? Integral of v1. So v1 is sin n pi x by n pi. Integral of this is, integral of sin n pi x is minus cos n pi x by n pi. Already we have 1 n pi there. So it becomes minus cos n pi x by n square pi square. Then plus u double dash v3. What is u double dash? U double dash is derivative of u dash, that is derivative of minus 2x. It is minus 2 and into v3. v3 integral of v2, that is integral of minus cos n pi x by n square pi square. Integral of cos n pi x is sin n pi x by n pi. So we will get v3 minus sin n pi x divided by n cube pi cube. So if we differentiate minus 2, next term we will get 0. Derivative of minus 2 is 0. So we will get next term as 0. So we stop here, apply the limits from 0 to 2. Put x equal to 2 first, then put x equal to 0. If you put x equal to 2, we will get sin 2n pi divided by n pi. We have sin n pi value is 0. So for any n, so value of sin 2n pi is also equal to 0. Next put x equal to 0, lower limit will get sin 0. Sin 0 is 0. So this becomes, the first term becomes 0 at both the limits, upper limits and lower limit. Similarly, the third term containing sine function becomes 0 at both the limits. So apply the limit for the middle term. Put x equal to 2, will get minus 4 by n square pi square cos 2n pi. then minus, put the lower limit x equal to 0, we'll get this term becomes 0 at the lower limit. So in the next step we'll get an equal to minus 4 by n square pi square cos 2n pi. But what is the value of cos 2n pi? We have cos n pi is minus 1 raised to n. So cos 2n pi is minus 1 raised to 2n. So minus 1 power even number is always equal to 1. So we have cos 2n pi is 1. So simplifying we'll get an equal to minus 4 by n square pi square. Next we will find bn. So what is the formula for bn? It is 1 by L integral from 0 to 2L f of x sin n pi x by L dx. Substitute for f of x and L, we will get bn equal to integral from 0 to 2 1 minus x square sin n pi x dx. Now take first u 1 minus x square as u and sin n pi x as v and integrate by using Bernoulli's rule of integration. So we bn equal to 1 minus x square minus cos n pi x by n minus 2x into minus sin n pi x by n square pi square plus minus 2 into cos n pi x by n cube pi cube. Put the limit x from 0 to 2. At the upper limit x equal to 2, the second term, the term containing sine function becomes 0 at both the limits, upper limit and lower limit. So apply the limit for the first and last term here. So we'll get simplifying bn becomes equal to 4 by n pi. Okay, next we will substitute the values of a0, an, bn in the Fourier series. So we'll get first term f of x equal to first term a0 by 2. a0 is minus 2 by 3, so a0 by 2 minus 1 by 3 plus summation minus 4 by n square pi square cos n pi x plus summation n from 1 to infinity 4 by n pi sin n pi x. So this is our required Fourier series expansion. Next let's solve this second question. F of x equal to find the Fourier series of f of x equal to half of pi minus x in the interval minus pi to plus pi. So here what is the period of given function f of x? How do you find the period? Period is equal to pi minus pi. So it is 2 pi. And we have also period 2L is equal to 2 pi. So L equals to pi. So Fourier series for f of x is f of x equal to a0 by 2 plus summation n from 1 to infinity an cos nx plus summation n from 1 to infinity bn sin nx. How do you get this? In the general Fourier series, take L equal to pi. We have f of x equal to a0 by 2 plus summation n from 1 to infinity an cos n pi x by L plus summation bn sin n pi x by L. In that general series, take L equal to pi. Okay, so we'll get this series. So from this, next we'll find a0, an, bn from given f of x using Euler's formula and formula for a0. General formula we have 1 by L integral f of x dx, but here for given f of x L equal to pi, so it is formula becomes 1 by pi integral f of x dx, and the limits for integrals are endpoints of the interval, that is minus pi and plus pi. So here integral of pi is pi x, integral of x is x square by 2. So in the next step we will get simplifying a0 equal to pi. Next we will find an. An is equal to 1 by pi integral from minus pi to pi f of x cos n pi x by L becomes, taking L equal to pi, we will get cos nx. So substitute for f of x 1 by pi integral minus pi to pi half pi minus x cos nx dx. Use general rule of integration by parts. and integrate taking u equal to pi minus x, v equal to cos nx. So we will get this 1 by 2 pi minus x sin nx by n minus 1 minus cos nx by n square. Apply the limits minus pi to plus pi. So first term we have sin n pi 0, sin minus n pi 0. So the first term becomes 0, and put the lower put the limits for term containing cosine. So we will get simplify this minus plus into minus. So we have minus 1 by 2 pi n square, and limit, apply the limits for cos nx. Put x equal to pi, you will get cos n pi, minus, put x equal to minus pi, cos minus n pi. But cos minus n pi is same as cos n pi. So we will get cos n pi minus cos n pi 0. A n is equal to 0. Similarly, find bn. Substitute the formula bn equal to 1 by pi integral minus pi to pi f of x sin nx dx equal to 1 by pi integral minus pi to pi half pi minus x cos sin nx dx. Substituting for f of x, integrate, and we will get 1 by 2 pi minus x into minus cos nx by n minus 1 into minus sin nx by n square. Apply the limits minus pi to pi. Second term contains sin, so if you substitute pi and minus pi in place of x, this becomes 0. So put the limits, put the upper limit x equal to pi here, so we will get pi minus pi 0. So the first term becomes 0. Put x equal to minus pi minus pi 2 pi into minus 1 by n cos n pi, and we have cos n pi equal to standard result minus 1 raised to n. Simplifying, we will get bn equal to minus 1 raised to n by n, and substitute the values of a0, an, bn in the Fourier series. We will get this as the Fourier series expansion of given function. Now look at this problem. Here function is given or defined in the range minus pi to 0 and then 0 to pi. So how do you find the period of the function? Period is pi minus pi, that is 2 pi. So here function is having period 2l equal to 2 pi, and we have l equal to pi, and first we will get the Fourier series expansion of function f of x. Then to get the series, to deduce the given series in the problem, we take a particular value of x from the given range of x and substitute in Fourier series of f of x, and we will get the required this given series. So first we will find the Fourier expansion of f of x. So the Fourier series of f of x defined in the range minus pi to pi having period 2 pi is given by f of x equal to a0 by 2 plus summation n from 1 to infinity an cos nx plus summation n from 1 to infinity bn sin nx. Find a0. A0 is 1 by pi integral from minus pi to pi f of x dx, and here note that function f of x is defined in two intervals, minus pi to 0 and 0 to pi. So we split the integral minus pi to pi into two parts. So integral minus pi to 0 and then 0 to pi. So 1 by pi integral minus pi to 0, where f of x is defined as minus pi. It's given in the problem. Interval minus pi to pi, f of x is from minus pi to 0. Function is defined as minus pi. So second term, from 0 to pi, function is defined as x. So integrate this. Integral of pi is pi x. Integral of x is x square by 2. So substitute the limits. For the first term, we have minus pi to 0, upper limit 0, lower limit minus pi. And for the second term, first upper limit is pi, lower limit is 0. Simplifying, we will get a0 equal to minus pi by 2. Next we will find an. Formula is an equal to 1 by pi integral from minus pi to pi f of x cos nx dx. Substitute for f of x, and for that we need to split the integral minus pi to pi into two parts, minus pi to 0 and 0 to pi. Substitute for f of x, and for the first term we have integral of cos nx sin nx by n, and second term we have x into cos nx. Integrate this using Bernoulli's rule by taking u equal to x and v equal to cos nx. So we will get in the next step 1 by pi into minus pi sin nx by n. Apply the limits from minus pi to 0, and here integrating using Bernoulli's rule, x into sin nx by n integral of cos nx minus here derivative of x 1, integral of sin nx by n is minus cos nx by n square. So for apply the limits, integral from 0 to here upper limit is pi, lower limit is 0. Put the limits, simplifying we will get so the terms containing sin vanish. So apply the limits for cos nx, simplifying minus 1 by pi n square cos n pi minus cos 0, taking x equal to upper limit pi and x equal to 0 lower limit. So this simplifies to an equal to minus 1 by n minus 1 divided by pi n square. Next we will find Bn. Bn is equal to 1 by pi integral from minus pi to pi f of x sin nx dx. That is 1 by pi splitting into two parts, minus pi to 0 pi sin nx, 0 to pi x sin nx. So integrate this. Integral of sin nx is minus cos nx divided by n. Apply the limits from minus pi to 0. Then integral of x sin nx is using Bernoulli's rule, x into minus cos nx by n minus 1 into minus sin nx by n square. Apply the limits from 0 to pi. So we will get Bn equal to, simplifying, Bn equal to 1 minus 2 into minus 1 raised to n by n. Next we will substitute the values of a0, an and bn in the Fourier series. So the required Fourier series is f of x equal to minus pi by 4 plus summation n from 1 to infinity minus 1 raised to n minus 1 by pi n square cos nx plus summation n from 1 to infinity 1 minus 2 into minus 1 per n by n sin nx. Next, to deduct the series given in the problem, we take x equal to 0 on both sides. So this becomes, Fourier series becomes f of 0 equal to minus pi by 4 plus summation n from 1 to infinity minus 1 raised to n minus 1 by pi n square cos 0. Cos 0 is 1. Next, plus summation n from 1 to infinity 1 minus 2 into minus 1 raised to n by n sin 0. Sin 0, 0. So this entire term becomes 0. So we'll get in the next step f of 0 equal to minus pi by 4 plus summation n from 1 to infinity minus 1 raised to n minus 1 by pi n square. Now, how do you find value of f of 0? So function is defined as minus pi for the interval minus pi to 0, and for 0 to pi it is defined as x. Okay, and f of 0 function is not defined at x equal to 0. So here we have 0 is point of discontinuity. And how do you get the values of of the function at the point of discontinuity? I have explained already about this. To get the, to find, how do you find f of 0? If here 0 is point of discontinuity, so f of 0 is the average value of right hand side limits and left hand side limit at the at x equal to 0. That is, f of 0 is half of f of 0 plus f of 0 minus, where f of 0 is 0 plus is the right hand side limit of function at x equal to 0, and f of 0 minus is the left hand side limit of function at x equal to 0. So we have f of 0 plus is, from the definition of function, f of x is x for 0 less than x less than pi. So for f of 0 plus is 0. Similarly, f of 0 minus is minus pi. So we substitute for these two in the next step, and right hand side we have 1 by pi, from the summation we can take outside the summation 1 by pi and put n equal to 1, we will get minus 1 power 1 minus 1 by 1 square, which is minus 2 by 1 square. Then take n equal to 2, we will get minus 1 power 2 minus 1 by 2 square. Minus 1 power 2 is 1. 1 minus 1 0. So we will get 0 here. Next take n equal to 3, minus 1 power 3 minus 1 by 3 square, that is minus 2 by 3 square, and so on. So minus 2 is common in all the terms. Take outside the bracket. So we will get this step. Next go on simplifying the both the sides. So we will get this. So finally we will get the required series. So pi square by 8 equal to 1 by 1 square plus 1 by 3 square plus 1 by 5 square plus etc. So students, some more problems on Fourier series we will solve in the next class. Thank you.